Today, we are discussing a response spectrum that we have to use in seismic design and analysis. This response spectrum concepts is very important because we always use a maximum value for design. For example, we have three engineering quantities: accelerations, velocity, displacement. But let's take this as an example. This is a accelerogram, which is a plot of acceleration as a function of time. Okay, this is what we know is a seismic motions or ground motions, right? You measure this acceleration when seismic activity occurs, and this is very important. But it is not possible, or it is not very practical for engineers to use all this time history analysis, because this time is very long, sometimes maybe 30 seconds and 40 seconds. So the time history analysis may not be that practical when the time lasts long, something like this. So what engineers has proposed is that they use only maximum value. For example, they use only maximum value, which is indicated by 0.3 G in east direction, for example, and they've used a 0.32 G in west direction, or north direction, or south directions. Okay? So this is a concept of response spectra. Okay? So they only pick up the maximum value. You can use acceleration, velocity, displacement in design. That doesn't matter as long as you have a proper engineering software. That doesn't really matter. But the problem is you have to use only maximum value. You're only interested in getting maximum value and getting maximum values. So in these two cases, your maximum value is here, right? So 0.32. This is your maximum value. So we call this value peak ground accelerations. Peak ground accelerations. Let me write down. Okay, peak ground acceleration. So we just say PGA. You say this is PGA. Okay, peak ground accelerations. So we pick up peak ground accelerations. So we have three types of peak ground accelerations, right? First one, acceleration and velocity and displacement. So now let's take a look at how we're gonna plot the spectrum plots for all of them: acceleration, velocity, and displacement. Let's take x-axis representing period. Okay, this is period. And y-axis represents spectral accelerations. This is acceleration axis, but we put spectral because this is a seismic value. Spectral, you could say this is a seismic value. So you will say spectral accelerations, and this is a maximum seismic values. Okay, so we just say spectral acceleration, or you could say maximum accelerations. They are same meaning. Okay, but engineers call this axis spectral acceleration instead of maximum accelerations in most cases. And x-axis, as I said, represents a period, right? So what happened? When t is equal to 0, what happens? when t equal to 0, which means that building is very steep. Building is very steep. When you go and t goes infinity, then what can you say? What can you say? The building is very flexible, right? So that t equal infinity means once you have buildings, and the vibration speed is forever, takes forever, theoretically. Go in and do not come back, right? The period is infinity means you go and do not come back, right? So this is very flexible buildings when at t equal infinity. Whereas t equal is 0, your building is very moving fast, back and forth, east and west and north and south. It takes almost no time, which means that your building is very fast, right? Which means your building is very steep. Remember, when your period is very short, your building gets very steep. It's called like, vibrate like this when your building is very steep. Whereas your building gets very flexible when it takes long time to come back and complete one cycle, right? So don't forget the meaning of t equal 0 axis and the meaning of t equal infinity axis. Understand? One more time, please. Okay. T equal 0 axis means the building is very steep, so the building comes back and complete one cycle in a very short time. And when t equal infinity, building is very flexible, so it'll take a long time for building vibration to complete one cycle. Understand? So we don't have these two extreme cases in most cases, right? We have probably somewhere in the middle of these two extremities. Right? So let's take a look at how we understand response spectra. In understanding response spectra, we don't need any mathematical formulations. Probably we'll take a look at a mathematical formulation to calculate the shape of response spectra, but not really. We first of all have to understand the physical meaning and how we can construct the shape of response spectra. Okay, let's say at very stiff side of the building where you have a very stiff building, I should draw probably something like this. Your building is very steep, right? Let me draw something like this. And your stiffness are really great. But here we represent the building at this side, something like that. So your building stiffness is very weak, very weak. Instead, all the masses are lumped right there. You could say here your building lumped as well. Your stiffness is very strong, like this. Right? And okay, I should say that let's change the math. The math very small. Okay, so this is the case where we represent this end. This is the case we represent this end. Okay, so in these two cases are the extremities, and mostly we are in the middle. So what happened here, when your stiffness is very flexible, what happens? Let me try to put clear diagrams for that. Okay, erase it. See, okay. Let's say we have very stiff building, and we have here earthquake like this. Okay, we have very steep building with big stiffness and small mass. So this represented by big stiffness K, small mass. Okay, small mass. small mess, big K, small mess, big K, small mess. It is very stiff building. And you have a earthquake, seismic motions into that very stiff building. Then what's happening? Your top of the mass here, if you're stay over there, then what you're feeling is exactly what earthquake brings, right? So you're just shaking, you're moving together with the earthquake motions, right? Because your building is very stiff. What you feeling is what your earthquake brings you, right? So you're if you're checking your motion at right here, you have a same earthquake motions here. Right? So this, and this are same. Okay, do you understand? When your building is very stiff, when your building is very stiff, this and this are same. Do you understand? Okay. So what happened is, since we are interested in maximum value of seismic motions, whatever they are accelerations, velocities, and displacement, don't care. We just interested in, let me change the color if I can. Okay, here maximum value right here. Maximum value right there. Okay, maximum value right there, and you have maximum value right there. Okay, so when building is very steep, your maximum value that you can feel in your building is same as the maximum value that earthquake brings. Do you understand? Okay, do you want me to explain more time? Okay, when building is very stiff, the maximum acceleration or velocity or displacement or whatever, the maximum value you feel on your building is exactly identical to the maximum value that earthquake brings, right? So this value and same this value, right? So here, when you have a zero period, then you will see this value. This is what you feel. Okay, this is what you feel. This is this value. So what you feel here is the value that your earthquake brings, right? So this is PGA. Okay, so this what did I say here? This value is called a PGA, peak ground accelerations, right? Peak ground accelerations. So peak ground accelerations are what you are feeling on your building when your building is very stiff, right? So here, this point at intercept in y-axis at 0, this value is the PGA. Don't forget that, all right? So this is PGA. Understand? And we'll take a look at the other side of the diagram right there. Right there, building is very flexible. Okay, let me just start putting this way. So when you have buildings very flexible with big mass, when earthquake, what happens when earthquake hits your building? You're building something like that. Oh, so your building's right here, but your ground moving up here because your stiffness is very small, right? All your columns of buildings displaced as you show over there, as you see over there, because your building is very flexible, right? So if you're sitting here, if you're sitting here, you don't feel any movement. Why? Because you are actually stay still over there, whereas your building foundation moves back and forth because your frame is very weak. Can you feel? Or if you go this way, maybe here, right? Next movement, you feel your base over there, right? This is the inertial force, right? Okay, this is inertial force. Can you say that? Okay, so when building goes this way, when earthquake goes this way and stop it and change directions, right? And earthquake goes directions, change this way and change directions. Whatever they do, they hit you base of the building, but you don't feel any motions over there because your base of the building is just following ground, something like that. But this is extreme case anyway. It will not happen in reality. But as I said, this is a one far end, one extreme case is there. What happens when your building is extremely flexible with the infinite period, then you don't feel anything again. You understand? Okay. So this is totally opposite case that you see over there. Okay. So what happened right is then your vibrations, your motions that you felt, as I said, is what is that? Zero. Okay. So you're now talking no motion at all. No motion at all right here. Okay. So I'm gonna probably erase here. See the building with a curve. See, the curve goes zero here, right? Goes zero. Because you don't feel anything when earthquake hits your building, when building is very flexible with the infinite period. Do you understand? So we have these two cases understood, right? But what happened in the middle? And in the middle, the building behavior, the behavior vibration of the building goes up somewhere here and then reaches peak value. Okay, and then goes down. Right. So let me try to change the color. Okay, got it. So this is your maximum accelerations that you can feel in the building after it goes up and goes down. So what do you say this region? We say this region a resonance plateau. Resonance plateau. Resonance plateau. Okay, so we have increased earthquake loadings and we reach resonance conditions and the motion will diminish. Understand? So we can idealize a response spectra something like this. Okay, let me just plot here. Go. And your response spectra idealization looks like that. Go, plateau, go. Right? So here we have a spectral acceleration axis. X-axis represent a t, which is period. And what do we call this point where t0 axis meets y-axis again? What is it? Yes, PGA. Okay, this is PGA. And we go increase your acceleration to somewhere and reach a plateau. Plateau. We call this resonance. Resonance area. And we go down. Okay. And here, this is the general shape of response spectra. General shape of response spectra. So that we have to construct this response spectra and put them into Midas input.